Hello, and welcome back to Physics for the 21st Century. Again, my name is Greg Perugini, and today's topic, that's relative motion. What exactly do we mean by relative motion? Well, besides the obvious that motion is all relative to a given axis, what we exactly mean is that it takes a perspective to calculate motion. For instance, I am standing still at this moment, sitting still rather, and I'm sitting on the earth, and relative to the earth I am still. But we all know that the earth is moving, rotating on its axis. It's rotating around the sun's rotating around the galaxy. We got all these movements taking place. So and in fact, someone on Mars would look and say, I was definitely moving. So it's all a matter of a reference point. What I see as motion at another reference point might be seen as still. We have to take into account all actions on a motion and use vector algebra. This is an example. Say it's flying up here at 120 meters per second, let's say due north. Well, if there's a wind going in this direction at 20 meters per second, as far as the plane is concerned, it's going due north at 120. But if I'm standing here, what am I going to see? I'm going to see the plane being knocked this direction, am I not? How much in that direction? That is a question, right? We can even figure out the angle too. But let's just start with how much. Well, if this is 120 and this is 20, how do I get the hypotenuse of a triangle? Of course, Pythagorean's theorem, 120 squared plus 20 squared. What is that velocity? 121.7 meters per second. In my viewpoint. Again, according to the plane is going 120 meters per second. But the ground speed, according to the ground, of course, because it has an aiding by the wind, it's going faster. So we have to treat each component as a relative strength. Let's take another example, like a boat. This boat is being knocked off on an angle much the same way. So it's probably best to just take a look at this via a few simple examples. And let's just start with I have a plane. Well, the plane is going in this direction. Let's say it's going at 100 meters per second in the x direction, positive x. Let's say I'm standing on the ground. If I have a duck here, well, that duck, what does that duck see? If the duck is going 20 meters per second towards the plane, directly towards the plane, call that minus x direction, if you will. Relative to the shore, or to the ground, I should say, each of these have their separate. I see the plane going 100 meters per second. I see the duck going 20. But if I'm sitting in the plane, what do I see? How fast is the duck going? According to me in the plane, right? I'm stationary according to the plane. That duck is moving at an incredible velocity. I see this duck going. I see the duck going at 120 meters per second negative towards me, right? What does the duck see? Well, the duck is moving. According to that movement, the plane is moving at an incredible speed, 120 meters per second towards it. The plane is coming in. Let's look at another example. Let's take that boat example. But let's add another thing to it. I have a boat, and this boat is going 3 meters per second up this way. Got a little motor going up across the river from this point, and the river is 150 meters wide. And it's going due north, straight up north. We have a current. And that current is 2 meters per second. From due north, the question is, how far downstream when it reaches the shore? Again, if I'm in the boat, I'm just going up north. But for me on this shore, this boat is going off at an angle because of the current coming in this direction. So like we did with the plane example, I could easily figure out what this is here. My total velocity relative to the ground has an angle right? And this hypotenuse, you can calculate this out. No problem, right? But that wasn't what the question asked. I want to know this distance, this displacement. Well, that displacement is in the x direction. So I can calculate that, right? Because I first see I'm going 150 meters, and I'm doing that at 3 meters per second. We can write that down. Change in y is equal to 150. Velocity, initial, 3 meters per second. There is no acceleration. Right? So therefore the velocity final is going to be 3 meters per second. Now I can use the kinematic equations, but it becomes fairly easy if you just look at this at 3 meters per second. I am doing 3 meters for every second, and I have to go 150 meters. Well, that obviously then leads to 50 seconds it would take. If I have 50 seconds and I'm going 3 meters every second, that of course will cover the 150 in the y direction. Right? This is in y. But what I want is in the x direction. Well, in the x, what's happening? To figure out how much downstream in the x, I know I'm going to do that in 50 seconds. And I'm doing that at 2 meters per second because of the current. The amount downstream is 100 meters. Now you could have figured it out through ratios as well. This one tends to be a very easy example. So, in conclusion, keep your reference points in mind. What are they asking? From what reference point to what other reference point are we looking at? According to me on the shore, I see this going at 3.6 meters per second. But of course, the boat only sees and only knows of its 3 meters per second in the north direction. Remember, you can solve many of these problems using kinematics with each component strength in mind. I can break each of these components if I'm given the hypotenuse, of course, and break each of those components into its constituent strength and figure out, well, how much is the strength of the current, or how much is the strength of the current, and how much is the strength of the boat, if I was just given the hypotenuse. So there you have it, relative motion, all dealing with reference points. Depending on where you are, you're going to get a different point of view as far as how far or how fast something is going. Good luck.